Yeah, so my name is Peter Kampschroeder. I am a sixth undergraduate student here at the University of Texas, and my talk is on MRI contrast agents. Okay, so as kind of a brief overview, first I'm going to talk about some of the physical processes that go into MRI contrast agents and kind of like how they're used. Then we're going to talk about the present clinical agents, specifically here in the United States, and then some proposed future agents for various applications. Without getting too deep into it, and my own animation is not playing, but if you have a, come on, there we go. So if you have a collection of, in an MRI image, you have a collection of proton spins inside a large magnetic field, which provides a Z direction field. Then you use an RF pulse to knock them into this XY plane, and you measure their decay back up towards the Z field. While they're decaying, they can also spread out from each other. And so the spreading out from each other causes a decay in your XY magnetization that is characterized by a decay time T2. The returning back to the Z direction magnetization is characterized by a decay time T1. Okay. And what a contrast agent does is it changes those. And for clinical contrast agents, there are other types of MRI out there, but contrast agents are mostly used in T1 or T2 weighted images, where you will make things brighter or darker based off their T1 or T2. And so if you inject a contrast agent, it'll change the T1 or T2 locally. And so what I have here is a picture of someone's brain where they have injected into their bloodstream a T1 based contrast agent, and it gathers around where there's a region of abnormal blood flow, and it shortens T1, making a really bright spot where they have a tumor. And that's the basic clinical use of an MRI contrast agent. T2 contrast agents are not preferred because they actually reduce your overall signal intensity, but T1 equations, T1 contrast agents are preferred. So yeah, how you actually change those will you introduce either a paramagnetic ion or some super paramagnetic source. That's described by this really long Solomon-Bloomberg-Morgan equation, or at least one of them. I only really want to point out a few things here. Our overall decrease in T1 is going to depend on the total spin of what we're applying. It's also going to depend a lot on the relationship between our correlation time and this term here, which is going to be the correlation time times the precessional frequency of water at whatever field we've decided to apply. And in clinical fields, this term over here becomes essentially negligible because this omega squared is very large. For a paramagnetic ion source, which is the primary type of clinical agent used, which is the primary type of contrast agent used, this simplifies greatly down to where it's just a bunch of constants times the charge of whatever ion you have times its rotational correlation time. So more charge, stronger relaxation effect. So if you're actually designing a contrast agent, though, you need to also keep in mind that you're going to put this into a person. And so it has to actually congregate in an area of some type of clinical interest, and it needs to be relatively safe, and it needs to get filtered out of the body after use. The paramagnetic ions that have been used were the 2+ ion of manganese, which has a charge of 5. Wait, sorry, no, it has, these are mislabeled. It has 5 unpaired electrons, so a spin for 5. Dysprosium 3+, which has 4 unpaired electrons, and gadolinium 3+, which has 7 unpaired electrons. Gadolinium's 7 unpaired electrons cause it to have the strongest relaxation effects. And so nowadays, well, there have been other things used, and there have been some iron oxide super paramagnetic nanoparticles used. Nowadays, at least in the United States, there are 8 commercially available FDA approved contrast agents. Every single one of them is based around a gadolinium ion, and the gadolinium ion is what makes them work. Previously, there was one manganese one and two spion ones, but you can't buy them anymore. Problem with this is that they're based around gadolinium. Gadolinium doesn't work functionally at low field MRI, and high field MRI, the stuff they use in hospitals, is prohibitively expensive. It'll run you about $1 million per Tesla, and it runs 1 to 3 Tesla. Gadolinium itself is pretty toxic, and while the contrast agents basically bind it to reduce its toxicity, as more and more studies have been coming out about it, doctors have, I read a review from Health and Human Services that quoted doctors as being anxious or causing anxiety. So it's not unsafe, but like we could do better. We could come up with something else. All right. And this is just a list of all the FDA approved ones in the US. As you can see, all of them have gadolinium. So the rest of this talk, I'm going to be talking about other things people are trying to do with contrast agents, moving away from the ones that are currently in use. And so here is one proposed alternative. So this one is a iron oxide based nanoparticle system. They have this little glob of like biocompatible stuff, and then they slap a bunch of iron oxide onto it. And iron oxide has a relatively high magnetic moment, so you get a high relaxation effect. And importantly, these people were able to demonstrate that they got a T1 changing effect, and they were able to demonstrate higher resolution images through the use of their particular nanoparticle versus a available gadolinium-based contrast. So over here you have the gadolinium one, over here you have what they did in a rat, and you can kind of see finer vein structures becoming visible through the use of this particular contrast agent. Iron oxide is definitely one thing that people like to look for because it's a lot less toxic than any kind of gadolinium thing. It can actually be metabolized if it remains in the body. And in this study, they, to the limit of their equipment, they weren't able to detect it lingering around in their test subjects. But another thing that you could do is you could try to address the fact that gadolinium-based contrasts don't really function well at low fields, or other paramagnetic ions don't function so hot at low field. And so what this group out of NIST was working on, NIST was the other guy. What this group was working on was iron oxide nanoparticles, so just a little tiny clump of iron, and then running it at very, very low field. So here they're at I think 1.3 millitesla. And the benefit of going to a low field is that it's much cheaper. You can use permanent magnets instead of big, expensive superconducting magnets. The fields are weaker, so you can actually keep metal objects inside of a patient. And you can make a scanner smaller, more portable, etc. Problem is that your overall signal strength is lower. It scales with your magnetic field strength, so you're going to want some kind of contrast agent to improve things. And over here, I will point out that at a relatively low concentration of this zinc iron oxide based nanoparticle, so only 0.00325 millimolar, they got better results than this 0.16, I think, millimolar magnesium chloride using the paramagnetic ions. Manganese, sorry. The actual mechanism under which those work is kind of like this section I've circled here. Basically, the correlation time that they have ends up being much closer to the per-sectional frequency of water, so this gets larger than it would otherwise. And I'm running close on time, so I'll go kind of quick on these. But you could also do something completely different. You could stop looking at T1 and you could start trying to ask yourself, what if we looked at something else with our magnetic resonance? So one thing that happened, one thing that you can do is you can make these little discs and separate them by a varying distance. And what that will do is it'll alter the magnetic field for any water flowing through the disc. And in doing so, it'll alter the Larmor precessional frequency. It'll alter the frequency at which you see magnetic resonance. And so that's kind of illustrated in this picture over here, where you can see a frequency shift for the water flowing through disks of different geometries. And since you have a frequency shift, you can actually tell those different disks apart, and you could assign colors to different frequencies and create like a false color image. Particular benefits of these, because of the way that the water diffuses through them, they actually have a linear decrease in their magnetic field effects with size, not a cubic decrease. And so you can make them very small while still having a strong effect. And you can use them as like biomarkers, where you attach them to something you want to follow around, and then you just have to look for that frequency shift to find it. But I guess there's one thing to talk about very quickly. There was one further extension that this group also worked on, where what if we made these little disk arrangements change their shape depending on the local environment. So now we're not just looking at where our disks that we made a particular way are, we're looking at where the local environment has changed in some way. And so because the magnetic resonance effects that these have depend strongly on their geometry, if you replace the spacer in the middle with some kind of hydrogel that reacts to the local environment, in this case, local pH, you will change the frequency shift you get based off of local pH. Now your MRI is a three-dimensional non-invasive probe of acidity. And you could use that for other properties too. I saw another paper that is not in my sources, so I'm going to talk very lightly about it, of one where they had them actually like self-destruct and fall apart beyond a certain temperature. Yeah, so this is one of the other things that people are looking at. All right, I will open the floor to questions. So yeah, as a quick summary, MRI contrast agents, they alter T1 or T2 for easier imaging. Current contrast agents revolve around T1 based gadolinium based contrasts, and then kind of future things that people aim to do are like replace gadolinium, get better resolution, lower fields, or just do something new entirely. And here is kind of like the sources. These are all of the sources that made into the paper. I didn't talk about all of these, but they're all out there.